Hello everyone. Today, Shreyansh Manav Shukla of Bennett University, roll number E20CSE398, is going to pre present my topic implementation of HPC libraries for linear algebraic or matrix operation. So, so what really HPC is? HPC or high performance computing is an aggregation of computing power to solve problems which are either too large for standard computers or would take too long. It is also referred to as supercomputing for this reason. It enables the simulation or analysis of huge volumes of data that would otherwise not be possible with standard computers. The common challenge with high performance per computing is that you are processing more data than your infrastructure resources can handle, and you must wait for weeks or months to see the results, which typically delays the innovations and slows down the research. You can think of a you can think of a high performance computing system as a group of computer is called cluster, and each computer in a cluster is called a node. Each unit in the cluster has an operating system processor with multiple cores, storage, and networking capabilities, so the units talk to each other. A small cluster, for example, can have 60 nodes with 64 cores, which is 4 cores per processor, helping you solve a problem much faster. A supercomputer is a much larger variation of this HPC job that would run across on an on-premises cluster for 3 months, could run across 125,000 cores in 16 hours in the cloud at little or no incremental cost. So what HPC libraries are? Uh, there are many HPC libraries to compute performance based. So some libraries we will talk in this slide are CUDA, NumPy, Factorize, and Numba. So what CUDA is? CUDA is was CUDA. NVIDIA introduced CUDA in 2006. The term refers to two things. First, to massively parallel architecture of modern GPU with hundred of cores. NVIDIA, after introducing it has the term refers to have the massively parallel architecture. Modern GPUs with hundred of cores. First, to firstly, the massively parallel architecture of modern GPUs with hundred of cores. Second, first to GPU CUDA parallel programming model used to program these GPUs. We need some way that we can program all these cores efficiently and easily. So now we have CPUs with several cores and we have GPUs with hundred of cores, and we can use the two processors together as a heterogeneous system and get the best advantage out of each kind of a processor. So what are the benefits of CUDA? First, it gives this a way that we can efficiently process thousands of elements for tasks in parallel. Second, it gives us a way that nearby tasks can communicate and collaborate efficiently. So, and these heterogeneous system we have CPUs and GPUs, which together, which together can process many elements. Although I want to see CPU with several cores, each core is operating on operating on perhaps one or two threads. It and any given moment, whereas with GPUs, hundred of cores, each core is working on 10 or 100 of threads simultaneously juggling. So overall, we have thousands of threads that the working CPU is working with at any given time. So CUDA provides a scalable, intuitive way to express parallelism. We are simply write a program for one data element and it gets automatically distributed across our hundred of code for thousands of threads. NumPy vectorize. The concept of vectorized operation on NumPy allows the use of more optimal and pre-compiled functions and mathematical operations on NumPy array objects and data sequences, especially if you're doing stuff with scientific computing with big data, operating with statistic things like that, and it's called vectorization. The idea is that you have a big list of numbers and this could be a one-dimensional list or matrix or whatever. But just to keep it simple, let's say you have a big list of numbers from 1 to 1 million. For example, every number from 1 to 1 million, in our case, we just want to divide each of these elements by 2. No big deal. Now, how would we do that before knowing anything about what vectorization means? At all pretty straightforward. We would just write a for loop. We would say for every item inside my big list of numbers, go ahead and do I put the result back in the list or put it in a different list or something that will achieve my goal indeed. It will achieve your goal, but it doesn't take advantage of parallel computing capabilities as well as some other stuffs. We'll think about of a lot of modern computers. What that basically means is that if you notice what we are doing, it doesn't matter if you do one of these elements before a different one or if you do one chunk here and you do one chunk there. Each of these elements, when we do this division by two operation, is independent of each other. We don't care if they happen in a different order or simultaneously or not simultaneously. It really doesn't matter. And that's what vectorization comes in modern computer. Computers have a bunch of different processing units called cores. So you might have heard this terminology before. What we can do is take advantage of that by saying that we are gonna do a fourth of this list. Let's say for simplicity, let's just say we have four cores. We can operate we can operate independently on our computer. We can take 1 by 4 of this list, do it on one core, take a different quarter of the list, do it on different core. And then for the other two cores, also do quarter of the list. Now we have basically taken our time and divided by 4 because we are doing all four parts simultaneously and then execute the program, it will take less time. Now comes number. So what is number? Number is an open source JIT compiler that translates a subset of Python and NumPy code into fast machine code. It is just in time compiler. Now if I talk about number, guys, it is just like a just in compiler for Python. Okay, now when I say just in time compiler, we obviously know uh, we we obviously know and what say that is Python is slow programming language because it is an interpreted programming language. And if I consider some of the other programming languages like Java and C, they use this just-in-time compiler wherein they convert the entire code into the machine level code, right? Where in the case of Python, it is an interpreted programming language. It it gets directly executed. This conversion is not there, and because of this, Python is really slow. And compared to Java and C, what if there an option that we can make this Python code as just-in-time compiler? As a just-in-time compiler, or can we make it convertible into a machine code, right? And yes, we can do it by using this specific library called as number. So anyway, thanks for watching. Uh, hope you have understand few libraries, CUDA, NumPy vectorization, and the third number. Thank you.